Okay, so let's continue our discussion related to sequential circuit design. And in the last lecture, we had seen that in earlier lectures, we had been talking about combinational logic. And we had said that these digital circuits can be looked upon as decision-making systems, decision-making machines. And a combinational logic makes a decision which is based on only present value of inputs. And that's a limitation of the combinational circuits. A more general purpose decision-making system would be one that would make decision not only on the present values of inputs, but on the past values also. So it has a memory which it can use to arrive at better decision-making process here. And so this combinational logic then, for example, we could then improve this combinational logic as a decision-making system to this particular system here, where we still have a combinational logic, but Z is dependent not only on the present value of X, but we have storage elements or we have memory in the system. And Z is also then dependent on not just the present values of X, but the storage elements contain the past values of X also. Depending on the nature of the system, certain past values of X are also there. And that also feeds into the combinational logic. So Z is dependent not only on present values of X, but some past values of X also. So that's a better, when you have a system like this, then you can implement better systems using this particular approach. But even this one has some limitations, and let's illustrate that through the following process. So realize that all sequential circuits that we had discussed earlier, they were all synchronous sequential circuits in which everything took place according to the clock. And so we said all the data X that is coming in and the Z values that are there, they're all, they vary with the clock. And this N notation refers to the nth clock cycle here. Okay. So let's say we want to implement, just to illustrate the limitation of this particular system here, where Z depends on X and past values of X, implemented in this particular manner here, where only certain past values of X are stored here. So if you want to implement a system where, let's say, the output data is the input data which is coming in, and it's odd, OR operation is performed on with, let's say, the past values of the output here, right? So Z could depend on the present value of X and the past value of Z here. Now, we can obviously see that if we are storing only the past values of X, then what we'll have to do is we have to write Zn minus 1 as Xn minus 1, or with Xn minus 2, we can expand this. And we can see then that if we are storing only past values of X, then obviously we will need, if there's a continuous coming data stream, then we'll need to store all the past values of X that are there here. And then we require an infinite memory. If we have a real-time system and all the past values of X have to be stored, then you require a huge, almost infinite memory. And that's a limitation of this particular approach, where we are saying that we will have X and we will store only the past values of X, and Z depends on X and past values of X. So in this case, we realize that an easy way out is, well, why don't we store not just past values of X, but if required, past values of output also. So a more general system we could say is the following. It's a combination logic where Z depends on X, the present value of X, and past values of X, which are stored in this memory here, storage elements, and past values of Z also. So depending on the nature of the system, in some cases, maybe past values of Z is not required. And so that's fine. But a more general system would be where the output Z depends on present value of X, past values of X, and past values of Z. Right? So that's a more general system. Well, even here, we can point out certain limitations here. So for example, let's say you want to implement a system where Zn in the nth clock cycle, which means, let's say the present clock cycle is clock cycle number n. So Zn is Xn, ORed with Xn minus 1, ANDed with Zn minus 1. So in this case, then because you require a past value of X and a past value of output Z here, so you will require two storage elements, right? You have to store Xn minus 1 according to the approach that we have. right? The storage element will store the past values of x and the past values of z. And so here we have to store the past value of xn minus 1 and we have to store zn minus 1. So we require two storage elements. But we also realize that this is unnecessary because we can define a new variable, which is yn equal to xn minus 1 and it with zn minus 1. Why use two different storage elements? Because storage elements are expensive, they take up space. And so why not define a new variable called yn, which is xn minus 1 and it with zn minus 1, and then store yn, right? Store that into your storage element rather than xn minus 1 and zn minus 1 separately here. So what we see is the following. This is illustrating that we generalize our sequential circuit into this particular form here, where z depends on x here, the present values of x, and x and z are fed together, and a combinational logic is there which generates a value which is then stored in the storage elements. Note that it's perfectly general. If you want to store directly x, so that particular part of the combinational logic is just a short, you can directly store x. If you want to directly store z, well, that also can be done. And if some combination of x and z has to be stored, like in this particular case, that also can be stored here. And so z depends on x and the state of the memory here. So this is the memory here. So it depends on the present state of the memory here. And the present state of the memory may be related to the past values of x, the past values of z in some manner here, which this combinational logic combines them to create that the state of the memory here. So in simple cases, y could be simply equal to xn minus 1, y could be simply equal to zn minus 1, or it could be a more complicated combinations of the past input and past outputs are combined together in some manner by a combinational logic, and that is stored here. So the idea is that the output depends on the present input and the state of the system. And the state of the system meaning the values of the storage elements that are there here, or whatever is stored in the memory. So the values of the memory elements, that is what is meant by the state of the system here. So the output depends on present values of x and the present state of the system. Y represents the present state of the system here. So that's a more general description of a sequential circuit here. So and in this case we can we'll be able to implement more efficiently the sequential digital systems that are there here. So we can rearrange this particular form. So since z, note that if you go back, z, if you look at it here, z is a function of x and y here, right? So z is a function of x and y here. So this z that we are feeding in here into this combinational logic, well, we could remove this feedback here and we could do the following. We could just take y and feed it back here, because note that z is a function of x and y here, and what we are feeding in is x and z here into this combinational logic. So why not just feed y here? So if we feed in y here, that would take care of the z being fed there, because z is anyway a function of x and y here, right? So another way of doing the same thing would be in this particular manner. So there's no loss of generality. We can, instead of feeding z and combining with x using CL2, well, you can feed in y and combine it with x and then feed it into the storage elements here. So this is the way that we often conceptualize a sequential circuit, and this is redrawn in this particular manner here. So is the same diagram redrawn in this particular manner here. So note that z is a function of x and the present state of the storage elements. So the present state of the system. So x is a function of, z is a function of x and y. So this is z is a function of x and y here. And CL1 is what we are calling as the output logic, because it generates the output here, right? So we have given it a name now. Instead of calling it CL1, we call it the output logic here. So it's this particular part here. CL1 is output logic. Then the storage elements, we are calling it because it stores the state of the system. So we call it the memory, the state memory that is there here. And the state memory, if you look at it, what is stored in the state memory, what is stored in the storage elements come through CL2, right? So we call this the next state logic. So the storage elements are already there in let's say some particular state, And then the CL2 generates when the next clock cycle comes, the CL2 will generate what has to be stored in the next clock cycle. If something needs to be updated in the memory, CL2 will generate that. And so CL2 is what we call as the next state logic. So CL2 is gives this output to the state memory here. State memory is nothing but a set of flip-flops which will flip-flops are the memory for our system. So a set of flip-flops which will store the state of the memory here. And the next state logic CL2, note that it receives its input from X and Y here. So that is what is happening here. The next state logic. So it's a combinational logic X. It receives its input from the present state of the system and generates an output which represents the capital Y represents the next state of the system here. So this is what you want to be stored here. Once the clock cycle comes, once a new data X comes, corresponding to the new data X, you want to store new things in your state memory. So that's the next state of the system here. And the small y denotes the present state of the system here. So this is the block diagram of the sequential circuit, a very general purpose block diagram that can be used to implement sequential circuits here. And it has a particular name which we call it as a Mealy, named after the person who first described this particular block diagram of a sequential circuit. So this is called a Mealy sequential system or a Mealy sequential machine. All right, so it consists of three major blocks. There is a memory here. That's an important part of the system. We are talking about sequential circuits, so which have a memory here. And then the output depends on the present state of the memory, Y, and the present input X. So that is, and there's a combinational logic which decides how Z depends on X and Y. And then the memory keeps getting updated, and the next state logic decides how the memory gets updated. It generates the input for the state memory that is there. All right, so Y is the present state, small y is the present state, and capital Y is the next state here. There's another way of conceptualizing the sequential circuits is where note that Z is a function of, in this case, X and Y. And so the idea here is that Y is anyway function of X. So by suitably designing the next state logic, there's no need to feed in X directly into the output logic here. So even that is, the idea is that may not be required here because Y includes within it the effects of X that is there here. So the idea is that this connection can be removed and we can have this kind of a sequential circuit also. So this is also a general purpose sequential circuit. This is called a Moore sequential machine. And so both of them are equally in the sense that they can be used to design sequential circuits for any particular problem. They have their own advantages and disadvantages. We'll not go into those aspects. And most of the time we'll do our sequential circuit design using this particular approach, using Mealy sequential machine here. And in a few cases we may see where the Moore sequential machine is used. All right, so let's look at an example of a Mealy sequential machine here. So let's say we're given a system like this here. So in this system, you can recognize these are the storage elements here. The D flip-flops that you see here are the storage elements. And so let's map this sequential circuit that you see here into this block diagram here. So the first thing is identify the memory elements here. So these are the memory elements, right? And these are the memory elements. Z is the output. And so this is the next state logic here. The next state logic, note that A represents A and B are the outputs of the flip-flop here. So for the sake of clarity, the lines have not been drawn from the output to the input like this and from here to the input like this here. So A and B are these output of the flip-flop here. And so they represent, A and B represent the present state that is there here. So this is the present state here. X is the input here. So this is the next state logic here. This is our combinational circuit 2 here. Next state logic here. So this is generating the inputs for the flip-flop here. So when the next clock cycle comes, whatever is present on these two lines, that will then go to the output here, and the state of the system will get updated here, right? So this is the next state logic. And this part is the output logic here. So it generates the output Z, given the present state of the system. A and B represent the present state of the system, and present value of X, and Z generates the output here. So that's the output logic here. So this is an example of a sequential circuit where we can identify the state memory which is there implemented in flip-flops. There's a next state logic, a combinational circuit here, and there is a output logic here. All right, so let's analyze what does this circuit do. What is the output here? So given a circuit, we need to determine what its behavior is. And so that's the analysis part. And sometimes and very often we want a particular behavior, and then we would like to design a circuit that would generate that particular behavior. So the dependence of output Z on input X depends on the state of the memory. So the first thing is to look at the memory here. And the memory has two flip-flops, right? Two flip-flops here. And each flip-flop, the state of flip-flop here, A, can be 0 or 1. So there can be, the memory can, or the state of the system can be, there are four possibilities. The state of the system can be AB, can be 0, 0, 0, 1, 1, 0, 1, 1. So this particular system, because there are two flip-flops, can be in four possible states that are there here. And so to describe the behavior of the sequential circuit, we need to show how the system goes from one memory state to the next state as the input changes here. So note that as X changes here, the next state logic will generate the output here and will update the memory elements here. So we need to show how the state of the system changes as the input comes here. And we need to show how the output responds to this input that is there here, to change in the input that is there here, right? So that's what we are looking for in terms of the behavior of the circuit, how the state changes in response to the input and how the output changes in response to the input. And in this case, we have only one single bit input here. Okay, so let's do that here. So we can now, to find out how the state of the system changes, we need to look at these inputs to the D flip-flop here, because as the clock cycle comes, the whatever is at the input of the D flip-flop will go to the output here. So we need to find out DA. So I will not go into the details. It's easy to see here that DA will be equal to A times X. This is A times X. This is B times X here. So we can combine them up. So DA is AX plus BX. And similarly, DB, the data pin of the D flip-flop, is equal to A bar X here. And the output here, Z, is equal to A and B, A plus B, X bar here, right? So we can write down these equations here. And the next state of the system, next state. So let's say the present state A is A at the present time T. So the next time, T plus 1 denotes the next clock cycle. So the next state of the system will be nothing but whatever is the D value here. So once the clock cycle comes, the D will go, whatever is D will go to A. So AT plus 1 is AT. So basically this equation here. And the DB will determine the next state of the flip-flop B here. So BT plus 1 is A bar T here. And Z is A plus BX here. So we know how the system will change its state. Given the value of X, these equations describe how the system changes its state here. So we can show that in the form of a state transition table. If you want to describe how this state of the memory changes in response to the input, so we describe it as a state transition table here. So in this, A and B are the outputs of the memory and they represent the state. X is the input and then the next state here and then the output here, right? So the whole description of this particular circuit can be captured in this state transition table here. It is there in this in these equations also, but it makes it more explicit as to what happens here. So let's say the present state of the system. So the possible states of the system are 0, 0, 0, 1, 1, 0, 1, 1. So let's suppose the present state of the system is 0, 0. So present state of the system is 0, 0. Suppose we receive X equal to 0. So input is X equal to 0. What will be the next state of the system? Well, we can use this equation here. So we can put A equal to 0, B equal to 0. And so therefore we can see the next state of the system will be A will be equal to 0. And then what will be the next state of the system B? Well, we can put here A bar and X is 0. So it will be basically 0, 0 here. So if the system is in the state 0, 0, and if the input X is 0, the system stays in the same state. It stays in the same state. Next state is also 0, 0. What is the corresponding output? Output is Z A plus B is 0 here. OR with B is 0 here, so Z is equal to 0 here. Now, if the present state is 0, 0, and if the input X is equal to 1, so again, we can use these equations to find out what happens here. So we'll not go into the details here. If you can see that the A will be 0 and B will be 1 and Z equal to 0. This means if the system is in present state 0, 0, input X comes in as 1, then the system will go to the next state, which is 0, 1, and the output will be 0 here. So like that, we can fill it up here for each combination here. So next we think of, suppose the system is in 0, 1 state. And then if X is 0, what happens here and what happens to the output? If X is 1, what happens to the next state here and what is the output here? Then we think of the other state here. Suppose the system is in 1, 0 state here. Then in 1, 0 state, the input could be X could be 0 or 1, and those possibilities we fill it up. Then the other possibility is system is in 1, 1 state. If input X is 0, what happens here? 0, 0, 1, 1, what happens here? Here, and we fill up the table here. So this is called the state transition table. It tells us how the system goes from one particular state to the next particular state given a particular input, and what is the corresponding output when that happens here. Okay, so that describes the behavior of the system that is there here. Now we can describe this behavior. This is in the form of a table, and we can describe this system in a more compact and more easily understandable form, which is in the form of what we call as a graph here. So instead of a state transition table, we can describe it in the form of a state transition graph. Okay, so let's see here. So the state 0, 0 here. So we describe the state A equal to 0, B equal to 0 as a circle, and we can write that this particular state is 0, 0, and meaning A has a value 0 and B has a value 0 here. Fine. So we have 0, 0. The system is, let's say, in this particular state here. Now we get an input X here, X equal to 0. So when we get an input X equal to 0, two things happen. The system goes into some other state here, right? Some other state, and there's a certain output that we get, right? So we can now we can see the table that if we have 0, 0, and if X is 0, the system goes to the same state and the output Z equal to 0, right? So the system stays in the same state. So we can on the other hand, when the system is in 0, 0 state and we get a 1, then again the system will go to some other state and there would be an output here. So these first two entries that you see here, the first row and the second row, the first row can be described by these two, and the second row can be described by these two here. So let's do that here. So note that if the system is in 0, 0 and you get X equal to 0, then what is the output? The output is 0. So we write 0/0. So the first one means the input, and after slash it means the output. Okay, and the system stays in the 0, 0 state here, right? So we have an arrow which goes like this here. So what this means is the system is in state 0, 0. If it receives an input 0, then the output is 0 and it stays in the same state here. Well, how do we describe the second row here? Well, the system is in 0, 0 state. If it receives a 1, output is 0 here. So 1/0 here, and it goes into a new state which is 0, 1. So we describe a new state with a circle and 0, 1 here. So the first two rows, we can describe it in this particular manner here. Now we focus our attention on 0, 1. We focus our attention on the third and the fourth row. So if it is in 0, 1 and it receives a 0, then it goes to 0, 0 state here, and the output is 1. So you can describe it again in this particular manner here. Okay, so using this particular approach, you can practice and show that the state transition table can be mapped onto this particular graph here. So all the transitions that you see here, so all the states are here. There's a 0, 0 state, 0, 1 state, 1, 0 state, 1, 1 state here. And so all the information that is here is mapped onto this particular graph here. So for example, this tells us if you are in the 1, 1 state. If you are in the 1, 1 state and you receive a 1, if you receive a 1, you go to 1, 0 state. So note that if you are in the 1, 1 state and you receive a 1, you go to 1, 0 here, and the output is 0. So the output is 0 here. On the other hand, if you're in the 1, 1 state and you receive a 0, you go back to the 0, 0 state here. So if you're in the 1, 1 state, if you receive a 0, you go back to 0, 0 state here, and the output is 1 here. The output is 1 here. So the entire table is captured in the form of a graph here, and the graph makes it easier for us to understand what this particular circuit is doing here. So so from this particular graph, I leave it for you to see that this is the behavior of the circuit here. That X is a continuously coming data stream, 1-bit data stream, and this data is coming in sync with the clock. So say the data comes in like this here, and look at this particular state transition graph and convince yourself that what this particular graph is basically doing, what the system is doing is that the system is generating an output Z equal to 1 every time it sees a sequence like 1, 0 or 1, 1, 0 or 1, 1, 1, 0. So when a particular sequence of numbers is coming, it's generating a output Z equal to 1 and detecting that particular pattern in the input bit stream here. Right, so in the analysis, then what we have done is the following. Given a circuit like this here, we've identified what is the state, which are the memory elements, and which is the next state logic and which is the output logic. From there, we got the equations for the next state logic, and we got the equation for the output here. And from there, we can convert it into a state transition table and then map it onto a state transition graph, which then helps us understand what this particular circuit is doing. Now, this is analysis. In the design, we do just the opposite. Given the behavior of the circuit, we try to capture the behavior of the circuit into a state transition graph. And from the state transition graph, we try to go to a state transition table and use that to design the circuit that is there. All right, so let's see examples of that. So from the specifications, whatever is the nature of the problem, from the behavior that you want to represent in the form of a circuit, you try to get the state transition graph. And once you have a state transition graph, you choose a particular flip-flop type. You do a state encoding, you get a state table, and then you synthesize the two combinational logic circuits, the next state logic and the output logic. All right, so let's see what we mean by that. So the specifications are, from the nature of the problem, we want to capture it in this particular way, a state transition graph, and then the state transition table, and then finally the circuit here. Okay, so that's the approach to designing the sequential circuit. So the first step is the state transition graph. So all right, so let's see with some examples. So suppose we want to design a sequence detector, and the goal is to detect 3 or more consecutive ones in the input stream. Right, so every time 3 or more consecutive ones occur in the input stream, the output Y should go as 1. So how do we describe it in the form of a state transition graph? So right now, let's suppose we use some symbols for the state here. So let's say my system is in, when you switch on the system, let's say it starts off in a state called S0. Fine. If I receive a 0, note that its goal is to determine a sequence of 3 or more ones. So if I receive a 0, I stay in the same state here. If I receive a 1, output is 0. Note that output has to go 1 only when it has detected 3 or more ones. So it has a 0 has come, so the output is 0. 3 ones have not occurred. I get a single 1, I go to the next state, S1, meaning that a single 1 has been detected, but the output is still 0 here. Now when I go to S1, two things can happen. The input can be 0 or 1. So if I get a 0, then I come back to here, because we are looking for 3 consecutive ones. So that pattern is broken. So I come back and I wait for a 1 again. So 0 and back to 0 here. If I get a 1, then I go to state S2. S2 denotes that 2 ones have been received, but the output is still 0 here. Now if I receive a 0, the pattern gets broken again. So I go back to a 0 state here. On the other hand, if I receive a 1 here, then the output immediately goes 1. Why? Because we have received 3 ones now, and it goes to state S2. And then in S2, if I receive a 0, I go here, back to S0 here. On the other hand, if I receive a 1 here, it stays back here and keeps generating 1. Because any 3 consecutive ones, the output has to be 1 here. So it keeps generating here. Right? So what we see here is that through the state transition graph like this, by looking at the nature of the problem, we can try to solve that particular problem by thinking in terms of the states of the system here. So we start off from some default or a let's say a state of the system S0, and then we see in response to the input which state should the system go to and what should be the corresponding output, such that the problem of let's say whatever it is the problem that we are trying to solve, the problem is solved by going through these set of different states in response to these inputs that are there here and the corresponding outputs that is there. And okay, so this is how we arrive at a state transition graph, basically mapping the nature of the problem onto a state transition graph. So now let's look at how do we convert a state transition graph to a circuit. So let's start with a very simple example here. So let's say we have a state transition graph with 2 states here. So S0 and S1. So we initially start with states represented in the form of a symbol, S0 and S1. And so let's say this is the state transition graph. And we would like to map it onto a circuit now, right? So circuit meaning we need to decide, first of all, note that to design the next state logic and the output logic, both of them require the output of the memory. So the first thing that we do is we start off by defining the memory. Okay, and defining the memory means we have to decide first how many storage elements do we require here. So in this system, we have 2 states here. And so 3 blocks need to be designed. So we start off here. So how many storage elements, or each storage element is a flip-flop. So how many flip-flops do we need? We have only 2 states in the system. So note that if you have n flip-flop, it can represent 2 to the power n states. Because 1 flip-flop can represent 2 states, 2 flip-flop can represent 0001, 1011, 3 can represent anything from 000 to up to 111, 8 states here. And n flip-flops can represent 2 to the power n states here. And so if we have only 2 states, then, well, we can use only 1 flip-flop. And note that in general, we may want to use as few flip-flops as possible because everything takes up area and flip-flops are expensive. And therefore, we would like to use as, just like flip-flops, the next state logic, we would like to minimize the complexity of everything in the circuit. We would like to design as simple a circuit as possible. And many times, if we choose the minimum number of flip-flops, many times what happens is, at least in simple cases, this, if we look at the overall complexity of the circuit, this one may be the most complex block, and the next state logic and output logic may not be that complex here. So your goal is to minimize then the number of memory elements, and therefore we choose the minimum number of flip-flops. So in this case, how many flip-flops do we need? Because we have 2 states, we need 1 flip-flop. The next decision that you have to take is, which kind of a flip-flop do you choose? Because remember, we had a D flip-flop, we had a JK flip-flop, we had a toggle flip-flop T, and there could be other flip-flops that are there here. So those are the common ones: D flip-flop, JK flip-flop, and the T flip-flop that is there here. So those are the common ones. We have to choose amongst these 3, one of them. And D is a very simple flip-flop, and implementation using D flip-flops takes less effort as compared to others. So let's suppose right now we'll show you. It's not easy to decide which flip-flop to use. We'll just show you that there can be potential differences in terms of, the impact would be there depending on which flip-flop you choose. So let's say we choose D flip-flop here. The next thing is, note that right now these are symbolic states, S0 and S1. Now we have to describe these states in terms of the output of the flip-flops here, right? So this is called the state encoding. For example, the states are represented by the outputs of the memory here. So now what is S0? We have to assign that. So for example, there's only one D flip-flop, and we can say Q equal to 0 when output of the flip-flop is 0, that represents state S0. And when Q equal to 1, that represents state S1. Note that we have a choice here. We could have said Q equal to 0 represents S1, and we could have said Q equal to 1 represents S0. And the choice has then some implication on the complexity of the circuit, but we'll not get into those. Are advanced topics. We'll not get into those. So right now, it's sort of you could use you know, Q equal to 0 or Q equal to 1, anything to represent S0 and S1. We'll not get into the details of that here. So fine. So we have chosen we said that because there are two states, we require one flip-flop. The second thing is we've chosen a D flip-flop. And we've also said S equal to S0 will be represented by Q equal to 0, and S1 will be represented by Q equal to 1. Okay. So now the memory is defined. Now we have to design the next state logic, and we have to design the output logic here. And so we do that through the state transition table here. So state transition table, this is a part of the state transition table. So column 1, 2, 3 is the state transition table. The last column shows you the output Z that we get in correspondence to the input that we get here. So basically the state transition graph is mapped onto the state transition table. So note that, so the S0 is nothing but Q equal to 0. So let's say you are in S0 state, so Q equal to 0, and you receive an input 0. So what happens if you receive an input 0? You stay in S0. So the next state of the system is 0. Qt plus 1 is 0. And the corresponding output is 0. Okay, so from basically here. If you are in state S0 and you receive a 1, then you go to state S1. So if you are in 0 here and you receive a 1, you go to the next state, which is S1, which is equal to Q equal to 1 here. So we put 1 here. Output is still 0 here. So we put 0 here. Next, you are in S1. So we have exhausted. We started with the state and we looked at what happens when X is equal to 0, what happens when X equal to 1. Fine. So that's over for this particular state. Next, we go to S1. So when you are S1, S1 is represented by Q equal to 1. If you receive 0, you stay in the same state. So Qt plus 1 is 1. Output is 0 here. On the other hand, if you are in S1 and you receive a 1, then you go back to S0. So if you receive a 1, you go back to 0. So this is 0 here. And the output is 1 here. So the state transition graph now is mapped onto a state transition table, right? But note that we have to design this next state logic, and the next state logic, the purpose is to generate the input to the flip-flop, right? Its purpose is to generate the input to the flip-flop so that once the clock comes, this flip-flop goes into the next state here. So we have to determine what value of D should be there to cause this, what value of D should be present here, so that the system goes into the next state here. So note that this is where you want to go from present state Qt equal to 0 to the next state Qt plus 1 equal to 0 here. So the input here D should be equal to 0. So if D is equal to 0, then Q will be equal to 0. Now you want to go from 0 to 1. So the input D should be 1. You want to go from 1 to 1. So D should be 1 here. You want to go from 1 to 0. So D should be 0 here. So now we can design the next state logic. Remember, this is a combinational logic. So its output is D, its input is X, and its input is the present state here. So we can write down an equation of D in terms of the present state Q and the input X here, right? So we can very easily, by looking at D in terms of present state Q and X, we can write down this equation here. So D is 1 when we have this Q bar X, and D is 1 when we have Q times X bar here. So this is D here. And we can write down the output logic. Basically, Z depends on X and the present state here. So Z we can write again in terms of Q and X here. So Z equal to Q times X here. So now we can implement it in the form of gates here. So we have this memory here. This is the next state logic, which is nothing but XOR gate here. So X and Q fed back here. And so this is equal to D. And the output logic is nothing but a AND gate here, right? So this is the circuit then. So we have seen how to take a state transition graph and map it onto a circuit like this here. So this is the circuit that will execute this state transition graph. All right, let's look at another example. Basically the same example. So we need to convert it here. How many flip-flops do we need? 1, Which flip-flop do we choose? So let's say we use JK flip-flop. And how are the states encoded? So again, the same thing. We can encode, say, Q equal to 0 represents S0, Q equal to 1 represents S1. So same way we encode here. All right, so now one single flip-flop, but this is JK. And the output of the JK flip-flop is the present state of the system here. And so now the purpose of the next state logic is to generate this J and K here. So JK flip-flop has two inputs, J and K. So the next state logic has to generate J and K so that the flip-flop, once the clock comes, the flip-flop makes transition to the right state here. All right, so that's the purpose of the next state logic. And output Z is a function of X and this one here. So we have to design these two logic here. So again, we need to write down the state transition table. So we had already written down the state transition table. So when present state input X equal to 0, it goes to the next state here. And output Z is also known here. So that part is already there. But to cause this, to make this transition from 0 to 0, right? So the J and K will have to have particular values here. And the combinational circuit has to generate those J and K here. So if you want to go from 0 and then you want to go to the next state 0, then what you need is this excitation table. This excitation table of a flip-flop. So excitation table tells us that if you want to make a particular transition, what is the input that you require in order to make that particular transition. So in the previous lecture, we had already seen that if you want to make a transition from 0 to 0, if the JK flip-flop is in present state 0 and you want to go to the next state, which is 0 here. So one possibility is 0, 0. X denotes don't care. So one possibility is 0, 0 because 0, 0 is the hold state. The other possibility is, well, you can apply 0 and 1 also here. Because if you apply 1 here, when J is equal to 0, K equal to 1, so it resets the flip-flop. Resetting means making the output 0. So it's already 0, so you make it 0. So that also is a valid input here. And so when you go from 0 to 0, then JK is 0x here. And similarly, you can see from the previous lectures that if you want to go from 0 to 1, then JK required is 1x here. Similarly, when you want to go from 1 to 0, it is don't care plus don't care and 1. And this is the excitation table. So this excitation table is useful in order to find out what values of J and K are required to cause a particular state transition. So you will use this excitation table. So that's something, for a D flip-flop, it was very simple. If you want to go from 0 to 0, the D value was 0. If you want to go from 0 to 1, D value was 1. For a JK flip-flop, it's a little bit more complex, but this is a excitation table is essential in order to design the next state logic here. So we want to go from 0 to 0, so we fill up 0x here. We want to go from 0 to 1, so we fill up 1x here. We want to go from 1 to 1 here, and we fill up x0 here. And we want to go from 1 to 0, so we fill up x1 here. So now, what is the next state logic? The next state logic has to generate J in terms of the present state and the input here. So we would like to describe J in terms of x and present state here. So I will not go into the details, but you can convince yourself that J equal to x and K equal to x and Z equal to QX here. Note that you can take advantage of the don't care states that are there here. All right. So this is the value here, and then our circuit becomes the following. Since J equal to x, so you directly convert here, K equal to x, you directly convert here, and Z equal to QX, so you particular AND gate here. So that completes the circuit here. So this was the state transition graph. When we use the D flip-flop, then this is the circuit that we got. On the other hand, for the same state transition graph, when we use the JK flip-flop, this is the circuit that we got here. And so if you compare the two circuits, it appears that the second circuit is simpler. In the second circuit, in the first circuit, we require an extra XOR gate here, while in the second circuit, we just have an AND gate here. So this is something that very often happens, that JK flip-flop may give rise to a more simpler circuit as compared to a D flip-flop. But designing with JK flip-flop is slightly more complex, because we have to look at what is the expression for J. In this case, it happened J and K are the same. but what is the expression for J and what is the expression for K, and we have to implement two logic here. One logic to generate J, another logic to generate K here. So it's a little bit more involved as compared to the D flip-flop. Note that D flip-flop may be simpler in design as compared to a JK flip-flop also. And so we'll not get into the details of that. Often in the problems that will be given to you, it would be specified whether you should use a D flip-flop or a JK flip-flop. But what we are trying to point out is the choice of the flip-flop does affect the complexity of the circuit. All right, so let's look at another problem, our example 3. So we have 4 states here, S0, S1, S2, S3. And if you note something about this particular state transition graph, we have only the inputs and there are no outputs here. Okay, so now you may be wondering that this is a funny circuit which has input but no outputs. But then in some circuits, the output of the flip-flop itself is the output. So if the system is in state S0, the flip-flop outputs will have a certain value, and that itself may be the output. So we don't have a separate output, but the flip-flop's output itself is the output. So it's not the circuit is not ridiculous in that sense. Okay, there's no explicit separate output here. So we have S0, S1, S2, S3 here. So we'll not get into what this particular circuit does for a moment, but how do we implement it? So we have 4 states here. So when we have 4 states, so we'll use 2 flip-flops. And to keep the effort required to implement this particular circuit simpler, we'll use D flip-flops. And let those 2 flip-flops, D flip-flops be, we'll give them a name, flip-flop A and flip-flop B here. Right? So we have 2 flip-flops, flip-flop A and flip-flop B here. And so all we need to do is, there's no explicit output, so all we need to do is design the next state logic. So the next state logic will have inputs coming from the present state QA and QB. And the purpose of the next state logic is to generate basically the DA and DB here. So this will decide how the system will go to the next state here. All right, so now these states are only symbols. So we have to describe S0, S1, S2, S3 in terms of the outputs of these 2 flip-flops. So let's say S0 is when A equal to 0, B equal to 0 here, which means the output of these 2 flip-flops 0, 0, 0, 1, 1, 0, 1, 1. Fine, so we assign these values here. Note that we could have assigned in different ways. And just like a different choice of flip-flop had resulted in different complexity of the circuit, a different state assignment may also result in different complexity of the circuit, but let's not get into those issues here. So the next thing is the state transition table. We start from a state, let's say 0, 0. And we say if the system is in 0, 0, suppose x equal to 0, what state does it go in? So we use this particular diagram here. If the system is in S0 and you give it a 0, it goes into the state S1. So state S1 is 0, 1. And so like that, we fill up the state transition table here, basically from the state transition graph. And once we fill up this table here, then we fill up, because our goal is to generate DA and DB. These are the inputs that are required for the flip-flop, and this is generated by the next state logic. So the next thing we ask is, suppose we focus on the flip-flop A. Flip-flop A has to go from 0 to 0. The present state is 0, the next state is 0. So what value of input D should be there? DA should be 0 here. B, on the other hand, has to go from 0 to 1. So what should be the input to B? DB should be equal to 1 here. So that's why D flip-flops are very easy. So in the next case, 0 to 0, so it is D is 0 here. For the B flip-flop, 0 to 0, so the input is 0 here. And like that, we can fill up what is DA and what is DB. And next thing is we want to find expression of DA in terms of QA. The present state is QA, QB, and X here. And similarly, we want to find expressions for DB in terms of the output of the flip-flop. So when we say A here, we mean QA. And when we mean B here, we mean QB here, okay? So we write down here. So we write down so for example, this describes DB here. DB here in terms of X, and AB. AB is QA and QB here. And this describes the DA here. So we know how to minimize using the K-map. And so these are the expressions for DA and DB. We'll not go into the details. And then we go ahead and implement it here. So those 2 expressions, DA and DB, are implemented in this particular manner, in this network of gates here. right? So that becomes the circuit which implements this particular state transition graph here. All right, so in summary, the synchronous sequential circuits can be described by this particular block diagram. By this block diagram, where we think of the system having a memory, state memory here, and then what we need to do is design basically these particular next state logic and the output logic here. So to start the design of a sequential circuit, we need to know what are the different states in the system, how many states do we require in the system, S0, S1, S2, S3, and how the system goes from one state to the another in response to the input, and how the output responds to these changes here. So to design this particular sequential circuit, we have to start from the nature of the problem and capture it in the form of a graph like this here, state transition graph. And that requires us to define the states S0, S1, S2, S3, and look at how the system goes from one state to the next, right? So this describes the input, and after slash describes the output here, okay? So this is where the design of the circuit begins. And then, of course, once you have a diagram like this, then you decide how many storage elements do I require. So we said that basically two flip-flops or two storage elements will describe 4 states, and 3 will describe 8 states. And so on that basis, we can decide how many storage elements are required. And once you decide how many storage elements are there, if there are 3 storage elements, A, B, C, then you have to now describe the states in terms of the outputs of those 3 flip-flops. A, B, C, meaning 0, 0, 0, 0, 0, 1. So we have to do, that's what is called the state encoding. So that is there. Then after that, you have to choose a particular flip-flop type, D flip-flop, JK flip-flop, or T flip-flop, whichever one is prescribed. So use that particular flip-flop. And then once you do that, then you design the next state logic, and then you design the output logic here, synthesize the output logic here through the state transition diagram, state transition table here. And all these, so this is what is called as a finite state machine. Another name for the sequential system that we are talking about is called a finite state machine here, because it has finite number of states, and the machine goes from one state to the next state in response to the input and generates the output here. So examples of finite state machines are all around us. The vending machine is a finite state machine. The traffic light controller is a finite state machine. And even your Intel microprocessor is a finite state machine, except that it does complex things in each one of those states that is there here. And it can perform a complex floating point division in response to a particular input that comes in. So it does more complex things, but at the heart of it is a state transition graph, a finite state machine, and it's a synchronous system. Everything takes place in sync with the clock. And so this is a calculator, this is a computer. So at the heart of all of that is a finite state machine. So let's stop here, and we'll look at a few more examples of a finite state machine in the next lecture.